So, the test. I received a few petitions by email, and I made some modifications, and as a result, the average on the test is now just very slightly over 75%. So I think that's pretty good, actually. 75% is like B, and B means, you know, not bad, you know? No, but like B is actually like what I expect the average to be around, so I'm pretty happy with that, actually. B is for bearable, yes. So, good. We need to continue on with our lecture material then. So we were talking, before the test, we were talking about resistor ladder digital to analog conversion. If you're going to talk in class, please keep it to a dull roar, please. Shh. Thank you. So, one of the interesting things about this circuit is, like, intuitively this may make sense to you, you know? Like, the most significant bit is always going to contribute half the voltage. It's the closest one to the measured output voltage. But we are scientists. We are not sufficient. It is not sufficient to merely look at something and have some intuitions about how it works. You must actually know. In order to analyze this circuit to determine that it actually works, you require a means of analysis called Thevenin Analysis. And I'm so happy that I have a chalkboard, because Monday I didn't have a chalkboard. So, Thevenin Analysis allows you to extract a piece of a circuit, rewrite that as a much simpler circuit, so that it can be worked with basically in terms of its output characteristics. This is similar to the idea of taking a piece of software code and putting it into a function, right? It's a way of modularizing. So this, I'm going to do a relatively simple example, such as the one that we got, you know, part of the way into on Monday, and then we're going to perform a Thevenin analysis over the digital to analog conversion circuit. Okay? Okie dokie. This stuff I'm about to do on the board is not in the slides, so you'll want to take notes. If you still have the capability, I don't know if you need paper to do that, maybe you have a device that does that. I don't know. We'll see. Anyway. How do you... That's high. Projector. Screen up. There we go. All right. So we had an electric circuit. Say this is 10 volts. Say this provides 2 amps. This is 10 ohms. This is 5 ohms. Feedback. Okay. And let's just put, another resistor here, and another resistor there, just for the sake of argument. Right? 5 ohms and 15 ohms. Right? Here's a circuit. The first step in Thevenin analysis is to identify that part of the circuit that you consider to be inside the box and that part which you consider to be outside the box. right? So in this case, I've already kind of hinted at the part of the circuit that we're going to consider outside the box. Basically, we're going to draw the box like so, right? So we will consider this part here. We'll call this VA. We'll call this VB. So with everything inside of the box abstracted, we end up with something that looks kind of like this. Right? Now, let's just connect that to ground, shall we? So, we have big old question mark going on in there right now. We need to figure out how this breaks down. Now, with Thevenin analysis, we always know that we will eventually result in a single resistor here in series with a single voltage source here. The question is, what's this resistance? What's this voltage? Right? So we'll call this VTH and RTH. So, incidentally, there is a parallel means, there's another form of this type of analysis called Norton Analysis, which replaces the voltage source with a current source and rearranges the circuit slightly. We're not going to get into it, but if you need a similar technique, a symmetrical technique that does the same thing with a current source rather than a voltage source, you're in luck because that exists. So, good. So, who can remember what the first step in calculating Thevenin resistance is? Yes?
I believe it's rewrite all the voltage sources as short circuits, and then current sources as open circuits, or as an open circuit, and then calculate the total resistance.
That's it. So, we rewrite this. That's the bottom one, actually, so. Boom. Voltage sources get rewritten as short circuits, or i.e. just lines. Current sources get rewritten as open circuits, or broken lines, i.e. they just get left out, and you just leave all the resistors in. Now, we want to take the equivalent, 5 and 15. This should be reasonably easy to calculate, right? Two resistors in parallel, in series with two resistors, right? So it'll be 1/10 plus 1/5 inverse plus 20. And if anybody can enter that into their calculator real quick? No? Yeah? Just shout it out when you get the answer. Anyway, this is the easy part, right? Calculating the resistance. The more difficult part is calculating the voltage. So with the voltage, we return to our original circuit without these things taken out, right? Yes? 23.3. 0.3 infinite. Thank you. So, we return to our original diagram. What we need to calculate is the voltage at these two terminals, the voltage difference. Of course, because we've connected this side to ground, VB is of course going to be 0, right? So we need to find the voltage at point A. Point A. Right? So how do we go about doing that typically? Starts with an N. First letter is NA. Yes? Nodal analysis. You guys have done nodal analysis, right? Yeah, good. You guys have done Kirchhoff's voltage and current laws? To death?
Yes.
Good. So, we have, our first step, of course, is to identify our currents, right? So, we have I1, I2, I3, I4, and I5, and I think that will do just about, we'll not worry about, well, we'll label it, why not? I6. So, let's call this point, point C. So the current law for point C, I1 must be equal to I2 plus I3, or sorry, I5, right? We can do point D as well. So I5 plus I3 is equal to I4. If we solve for I4, then of course we can figure out what the voltage is reasonably easily. Just RL is going to have to be known. So let's just make it 10. But there we go. So good. Excellent so far. So we can start substituting things. Let me just move this guy over here. So, some easy substitutions. First of all, we know that I3 is equal to 2 amps. So we can just substitute that directly and immediately. I don't know, is this actually useful or should we move on?
I just had a question about your currents. So,
Yeah.
never mind. I thought it was I3. Never mind. I read it wrong.
Okay, all right. Is this instructionally useful? Have you guys done Kirchhoff's stuff like this type of circuit analysis to death?
It's been a few months.
It's been a few months.
Good review.
Good review.
Yeah.
Who wants to continue this example? Who doesn't? All right. I'm sorry, you've been overruled. All right. So, just so you know, though, this isn't a democracy, because I'm in charge. This is a despotism, and I'm the despot. So, 2 amps, good. So we start subbing in. I2 is 5 ohms multiplied by VC. The I1, oh, this is gross. I1 is 10 volts minus VC. Wait, have I got that right? Let me see. It's I equals, oh my gosh. Am I forgetting Ohm's law? V equals IR, thank you. Yeah, thank you. So, my God. So it's VC divided by 5. Voltage drop there divided by 10 ohms. This guy is VC minus VD D over 5. There we go. Good, good, good. 10 minus VC equals 2 VC plus VC, 2 VC minus 2 VB. So we can say that 10 is equal to 5 VC minus 2 VB. Right? Good? Yes, excellent. Do this one next. So we've got that one. So I5 is actually this same I5 term from here. So VC minus VB over 5 plus 2 equals I4. I4 is, of course, both of these guys, right? So, well, it depends on whether you want to introduce the VA term, but why don't we just solve for this guy? Or maybe we can't. What do you think?
Where is I5 again? Like on the circuit?
Right there.
So why is it VC minus VB?
Well, because the current will be the voltage drop divided by the resistance. The voltage drop will be this voltage minus that voltage.
Yeah, so why is it VB? Isn't that D?
Did I write B? Oh, geez. Yeah, okay, thank you. Thank you. Good. Good. So, let's just do it. So that's 25 VD. Good. We'll just kind of keep I4 is equal to VD divided by 25. We'll just keep that one on spare for when we need them later. Right? So 5VC minus 5VD plus 2 equals VD. So 2 is equal to 6VD minus 5VC. Solve the set of linear equations. Oh, we've got more variables than we need though. Where's this B?
That's
Did I rewrite it again?
That's supposed to be D as well.
Yeah, thought so.
Also, where'd the 25 come from?
15 plus 20, or 15 plus 10.
Okay.
There we go. Thank you. I was about to say, I've got more variables than I have equations, and that's probably indicating a problem. So, yeah, okay. Sometimes it's, I don't like the equation subtraction method, but, you know, I don't know, it just feels wrong, you know? Anyway. So, 5VC minus 2VD minus 10 is equal to 6VD minus 5VC minus 2. I can tell I've lost the class as I do some basic algebra. So 8VD, oh my,
Why did the 2 not get multiplied by the 25?
I'm sorry, yeah. Can you tell it's been a while since I've had to do algebra? So, shut up. I don't care, shut up. Boom.
What about the 25 in the denominator?
Sorry?
The 25 in the denominator, like I understand you multiplied it by the VC minus VD over 5 and it gives you 5, but what about it multiplying by the 2?
Oh, yeah, that's true. Yeah, thank you. No, that's the wrong one. All right. Wait, no, it's 4. Yes. 4. Ah. So, 4 volts. Right there. Excellent. Now that we have that, we can sub that in here. VD is equal to 50 plus 5 times 4 over 6 is equal to 70 over 6, which is an improper fraction, or whatever it is. Yeah, where's my calculator? Did I bring a calculator? Let's see here. Yeah, 11.6 infinite sixes. 11.66, etc. Good. So we can take that here. I4 is equal to 11.66, etc. divided by 25. So just divide that guy by 25. Bing, bang, boom. 0.466, etc. So now we can take that, we can calculate what VA is, because VA, of course, is equal to 0.466, etc., multiplied by the value of the resistor 10, which of course is 4.66, etc. So we can say, ultimately, that the voltage, the Thevenin voltage here, is 4.66, etc. The Thevenin resistance is, what do we write down? 23.3, etc. Did I make a mistake?
I don't think you carried the negative sign from the -2 into the 10 PC.
Can we just move on? Yeah, is that okay? Yeah? Well, okay, fine. Which one? Where is it?
The 10
Negative.
equals 5.
Oh, yeah, this should be a, yeah, okay, so. Oh, all right, so
I wonder
20, so 20, so that means that this is 8, right? Yeah. 8 VC, 8 here, right? So that's 40, that's 90. That actually does divide evenly. Maybe it doesn't. Let's see. 15? Thank you. Yeah, that's true, isn't it? 15, there we go. This is 15 over 25, which is 3 over 5, which is 0.6. So 0.6, it becomes 6. Okay, volts, ohms. There we go. Good? Question?
What is like testable of this?
What is testable of this? I don't like to give people tests on exams that they haven't had in an assignment. But yeah, I think this would be fair game, doing a Thevenin analysis. Yes?
Are there assignments for this?
No, there aren't. I might post some practice problems though. Maybe that way I can justify putting it on the exam. Yeah. Question?
Is the exam in this room or in another room?
No, the exam will not be in this room. The exam is going to be done by the registrar with the desks in like IWC or wherever they do it these days. Any other questions? Okay, so that's all fine, good, well, and dandy. Now let's do it. Apply the same methodology to a more complicated circuit. We'll now do the DAC. So, let me just pull it up on my thing so I can all right. Okay. I'm only going to do 3 because that takes less time than doing all 4. So it's a slightly simplified version. So this is a 3-bit digital to analog converter using the resistor ladder method. Right? So the first thing that we need to do in order to understand this in terms of Thevenin analysis is rewrite it slightly so that it looks more like that, right? So these digital output pins we are going to approximate as voltage sources, right? These voltage sources, we're going to leave variables in here for the voltages because essentially we're modeling the pins as voltage sources which have a variable voltage, even though that variable voltage is either 0 or whatever high is, say 5 volts. Even though it's only 0 or 5 volts, that is still modelable via a voltage source with a variable for the voltage, right? A variable voltage source, if you will. So, the first thing that we can do is we can say VA, VB, VC. Beginning to look a little more familiar, right? So, obviously, this thing has already been set up with the 2 terminals at the end so that it looks like it's a Thevenin equivalent circuit already, right? Or, no, not that it's an equivalent circuit. It's pre-set up for a Thevenin analysis, right? However, in this particular case, it actually makes a lot of sense to subdivide the circuit and perform smaller Thevenin analyses on the internal component, like the internal pieces of the ladder. So, we're going to draw a couple of lines through this circuit and perform Thevenin analysis on sub-portions of the circuit. We're then going to compose that all together, right? So, we'll consider first just this part of the circuit. We will then consider just this portion of the circuit. So let's redraw that. So just that end bit. We've got voltage source, voltage source, there we go. That's not a voltage source, that's a resistor. 2R, 2R, right? So, First step, Thevenin analysis.
Source go bye-bye.
Voltage source go bye-bye. Yes. Well, yeah, okay. What's the equivalent resistance of this circuit? Yeah. So it's 1 over 2R plus 1 over 2R R inverse, right? So, yeah, if you were to do this out with algebra, it would be like painful. But yeah,
2 over 2R.
yeah, that's true. 2 over 2R, blah, doop doop, pop pop, deep dot equals R. There we go. All right, so R dH is equal to R. Good. So, what about the Thevenin equivalent voltage? Right? We redraw the circuit. Now this is, I don't know why I keep writing 5 there. Anyway. So, what does this look like to you? I might redraw this, right? It's a voltage divider, right? 2R here, 2R there. What's this voltage? VA over 2. Right? Good. So, our VTH here is VA over 2. Okay, good. So, let's iterate on this guy. So we now can simplify the circuit. VA over 2. R. 2R. VB. Oh, let's check that for VB. 2R. VC. VO. Right? So, let's do it again. So, redrawing just this portion using the resistances. Yeah. That doesn't seem right.
I think you forgot a resistor, like just
Yeah.
on the like where the line is, like the dotted line. There should be one up at the top.
Between VB and VC.
Oh, well, there's that one. Yeah.
But then there's also the Thevenin resistor.
Right, yes. Well, this is the Thevenin. That's the Thevenin resistor right there. Yeah, you're right. Yeah, thank you. I didn't copy the diagram correctly. Yep. So, yeah, there's a resistor there, and there's a resistor there, because this is the circuit. Yeah, okay. Thank you. Good, yes, excellent. So, we still draw our line there on this side of the resistor. Thank you. That makes it work. Good. So, in that case, we have VA over 2 with a Thevenin resistance of R in series with another resistance of R, which is, there we got 2R here, VB there we go. So Thevenin equivalent. What's the Thevenin equivalent resistance here? Add these two together, you get 2R, right? Then we're right back in that position, right? So the Thevenin equivalent resistance of this entire circuit is, once again, R. That is actually the whole way that this thing works. The thing that actually makes a ladder DAC work is whenever you look back in the circuit, the equivalent resistance of that circuit is always going to be equal to R. That way, as we're going to see, you get voltage division at every step, right? So, having figured that out, we now need to calculate the voltage here, right? So, we'll call this, I don't know, yeah, it'll be VTH, won't it? All right, so, so we actually only have the one loop here, right? So we only have one current. So we can, you know, we can use the loop law rather than the node law because we only have the one loop. So it's all of the voltages will sum to 0, right? So all of the plus voltages on one side, VA over 2, is equal to I1 R. Am I getting this very much? My God. All right. Well, 2R really. Plus the voltage drop across that one, which is 2 times R times I1 as well. And then you have on this side as well VB, right? Because it's opposing it. So VB is so. I feel like I've messed a negative here.
Does 2R in right in front of VB cancel out with the 2R after VH? Wouldn't the current be going? Oh no, I guess not.
They would be separate terms.
Would they cancel?
No, I don't think so. Jeez. What am I? Anyway. Must have set the equations up wrong. Kirchhoff's voltage law, all of the voltage, so this is a plus voltage, that's a minus, that's a minus, that's a minus. Does this count it, like, do I count that as a?
Yeah, that's a minus.
That's a minus as well, yeah. So, yeah, is equal to IR plus plus 2IR, which of course collected up is 4IR plus VB. So VA is equal to 8IR plus 2VB. Okay, good. So this guy, VTH, will be VB minus I times 2R, I think. Does that make sense? That voltage has to be, this is plus, that's minus, so we put them together, right? I'll do this out on paper first next time. Yeah. I thought it was easy. Oh well. So, isolate I. So I will be equal to over 8R VA plus 2VB. So take that, sub it. So VTH is equal to VB minus 2 times VA plus 2VB over 8 R.
Would it not be minus
R's
VB?
cancel. Sorry?
Would it not be minus VB for like when you're calculating I because you have to bring the VB over?
When you
Over here?
Yeah.
you put VB on the.
I think when you bring it over.
Oh, yeah, that should be, yeah. Good, all right. So that goes to 4. So VTH is equal to VB minus VA over 4 minus half VB, I think. Yeah. Plus. Yeah. Oh, right, because of the negative, yeah. So no, that can't be right. That doesn't come out right.
What direction are you going for like when you're making the equation for the Thevenin voltage?
This one?
Yeah, like how are you going through the circuit?
Just through here.
So wouldn't it be minus VB in the original equation? Because you're going from positive to negative.
That does make it come out correctly, so yes. Yeah, okay. Good, thank you. So, through much toil and tribulation, we now have, as our Thevenin equivalent voltage here, VB with a factor of 1/2, VA with a factor of 1/4. So, maybe you can just take my word for it that it works out the rest of the way equivalently. Because at this point, all you do is just repeat that same Thevenin equivalency, and this expression has each term added to it, and each one is successively divided by 2, right? So, does that make sense? Yes?
So would the next one be like VC over 2 minus VB over 4 minus VA over 8?
Well, this should...
I can't tell what that says from here.
Yeah. It should be a plus. That's the other problem. But at any rate, me and my negatives, I tell you. How did I miss the negative though? No, at any rate. That should be a plus. Yeah, so eventually, what you get is you get an equation for this that is VA over 8 plus VB over 4 plus VC over 2. Right? And if you had any more bits, then those would be added successively as well. Right? So, right? So that's how it works. Each time you take a step, you look down the ladder, and that ladder is divided, that divides the existing voltage by 2 and adds another one with a factor of 1/2. Does that make sense? Good. All right. Oh my gosh. Let's see how many slides we can cover in 2 minutes then. Yeah, I know, but we've got 5 more slides. So, no we don't. So you can also do this, you can perform this same analysis using superposition as well. Are you guys familiar with the superposition principle? Yeah? Basically, you hold one of these, you hold all but one of these at 0 at a time, and that allows you to calculate it on one of them at a time. You can sort of do it all at once, looking down it that way if you want as well. Good. So, by the time I actually put down the projector and turn the projector on, it'll be time for class to be over. So, yeah. Thank you very much for going through that painful journey with me. See you next week. Question?